Hey everybody, welcome to this week's Physics with Dr. T. I'm Dr. T, and we're going to be going over this week induction and transformers, more specifically magnetic induction of electromotive force. Magnetic induction may be one of the biggest and most pervasive factors of physics that we use in modern society these days. But before we get into the physics of that, let's talk about this week's pre-lab activity. In this week's pre-lab, we're going to be examining magnetic induction through simulation using a bar magnet that you see here on the page and some components that we want to use. Now, right now we're just looking at a bar magnet, but if we click on pickup coil, you see that we've got this device here that we can move around. This is some light bulb, some coil that goes around, and a magnet that we can move nearby it. And you can grab and move it, and you see that there are some changing magnetic fields near the coil. Simply double check your settings. You can have it as a voltmeter, you can have it as a light bulb. I'd say leave it as a light bulb. It just is a little bit more dynamic, a little bit more interesting. So we'll leave it at that. You see that you have the standard controls up here. We can increase the magnet strength on the bar magnet. We can decrease it, and it just makes it brighter or darker. So we can bring it all the way up to 100%. Just make it easier to see if you like. Flip the polarity if you're interested in checking that ahead of the lab activity today. I'd say go ahead and explore that. As this is intended to be a very simple, straightforward activity just to kind of give you a little bit of practice with the right hand rule, we don't need to make a lot of changes to the settings. Now, the instructions in the pre-lab guide say to put on the loop area be 50%, so we're going to leave it at that. It also says to change the number of loops to 3. It's the maximum that you can get on there. And I encourage you to change it down to 1 and then change it to 3 and look at how your changing motions are affected by having 1 versus 3 loops. So you simply grab your magnet, bring it close, and then bring it through at a steady rate and make observations about the light that you see flashing. That's pretty much it for that. Explore it a little bit, practice the right hand rule, make sure that you get a little bit of exercise with that. This is a fairly decent simulator, even if it is a little bit on the older side of it. For the second part of your pre-lab, just simply take your phone charger base, take a look at the back information. You'll notice that it's got input information, output information, and take a look at the instructions that are in the pre-lab to calculate the ratio of the number of coils for each part, the input and the output for your charger. You can also check your laptop and compare those as well. Mostly you just want to get a good sense of how how the transformers are actually built into your phone chargers. You want to get a sense of how the transformers that are used inside your simple charger, this is why they get so hot the way they do. Okay, so for the beginning of your magnetic field study, you've looked at magnetic fields that are basically static or at rest. Now we take a look at the fact of whether or not the field is in motion and what that does to other circuits. So the first thing we want to think about are field lines. What are magnetic field lines? Well, they're just like electric field lines or just like gravity field lines. They're not real. They're just a line that gives us a way of visualizing what the magnetic field looks like in that space. But in a region of space, there is a density of the magnetic field, just like there's a density of the electric field, just like there's a density of the gravitational field. And the closer you are to that density, the higher the magnetic field is. Well, we can use field lines to kind of give us a way of measuring that, and what we refer to those field lines passing through some point in space or some area of space, we refer to that as magnetic flux. We've seen flux before, electric flux, when we looked at the electric field lines passing through a surface. Now we're looking at magnetic flux. We're looking at magnetic flux in particular passing through a region of space, a surface area. And here I've drawn 2 surface areas that are similar in area. And you notice that the magnetic field is much higher closer to the pole than it is further away. And Faraday's law is, in fact, a change in the magnetic field, or more particularly the magnetic flux, through a surface area. And so we write magnetic flux as the magnetic field passing through that area. Now you may remember the dot product, we used it way back when we were looking at force times displacement. We called that work, so we got a scalar out of it. And we get a scalar out of it in this case. So the dot product, if you recall, we could write the magnitudes of magnetic field area and the cosine of the angle between those two. And for an area, like the area of my hand, the vector for that is pointing perpendicular to that. So as long as the magnetic field is passing through that surface, there's going to be some account of the flux through that surface. Faraday's law which is looking at the changing magnetic field in a space, needs to look at the changing magnetic flux in a region of space. And so we write it as this script E. N is the number of loops that might be present. And change in magnetic flux as a function of time is where the actual action is happening. And so we imagine a magnetic field moving this way. Right hand rule, thumb goes in the direction of the magnetic field, pushing this way. And now the magnetic field is increasing in the area bound by this loop. Well, as that magnetic field increases, there's a reaction of the electric charges. The electric charges don't know that the magnetic field is what's moving. And just like the Lenz's law, but what they want to do is move in a way that counteracts this magnetic field that's increasing. So they're going to move in a way that creates a magnetic field going this way. And if you remember from your third right-hand rule, the current goes in the direction that your right-hand fingers are pointing as they go around the loop when your magnetic field, induced magnetic field, is going in the direction of your thumb. So for this loop, if this is moving this way, the current is going in this direction around the loop. Okay, so now that we know that if we move a bar magnet near a loop, we induce a voltage that pushes the electrons and creates a current. But now, what happens if I bring a magnet that I've generated with the flow of electricity through a coil? Well, it should also have an effect on another coil. In particular, if we have a solenoid or a group of coils, loops, nearby where the magnetic field can pass through, we should be able to induce a flow of charges in this second coil. And in fact, this is the foundation of the transformer. The incident current, voltage applied across this, creates a current passing through this coil. The coil generates a magnetic field. Magnetic field is conducted to a nearby coil, which is not a physical part of the original circuit. And so the secondary coil has a voltage that's induced in it, and that voltage leads to a current that travels down that. Now, the very big fundamental part of all this is that this does not work for direct current circuits. This only works for alternating current circuits, AC circuits. And this forms a foundation of power transmission that gives us power, electricity, lights, and power for our phones and our laptops and medical equipment and all sorts of things. Again, we can talk about the magnetic flux between coming out of the coil 1 and going into coil 2. And so we look at the voltages that those two, based off of Faraday's law for both of those two coils. And we do make one big assumption. We assume that the magnetic flux coming out of the first coil goes into the secondary coil. I encourage you to think about how reasonable is that assessment. But if we make that assumption, then we can rewrite Faraday's law for both of those two coils, and leads to the transformer equation, which gives the output voltage in the secondary coil based off of knowledge of the number of turns and the input voltage coming into the primary coil. In this week's equipment, you'll be working with several coil packs and other components to be able to assemble both your transformers, but also to be able to use one of the coil packs for measuring your induced voltage. For the induced voltage, you want to use a 1600 pack, and you're going to use our good old Pasco voltage sensor in order to make the measurement that you're looking for. And of course, you just plug these in as usual. You'll use this fabulous catching tub. You'll simply hold your magnet, you'll simply hold your coil a little bit above the pad. You want to make sure that you've got enough space for that magnetic field to move far away enough from your coil pack, but you don't want to be too high up in the air. And you simply drop it through and test it a couple times. Just make sure that you get a nice smooth curve. When you move on to the transformers, you want to be a little bit more meticulous about how you set them up, because one is going to be plugged into your voltage current sensor, aka the output voltage. That makes this the primary coil, and then your secondary coil will still be connected to your voltage sensor so that you can observe the response in the secondary coil. Your first task is to have them join close to each other, and you make a measurement with your Pasco setting. Next, you'll make a measurement with a solid metal core. This is certainly going to just be iron. You run that in here, make your data run. Make sure you think about what makes the relative amp magnitudes what they are. What is it that this iron core is doing that makes the response of the secondary coil what it is? Third, you separate these two and you're going to mount them onto the iron core. Now it's tricky. You want to make sure that they're still facing the same direction to each other as they were before to try and have the most consistent series. So it'd still be to have the most consistency throughout your runs. So you see that this side is still facing this side. They just have now the iron core connecting going around. My suggestion is to hold this, lay it flat when you're making this measurement. You may even want to elevate it off the surface using your box to help hold it up to get better results. And you make your measurement, again thinking about what's going on, how is this compared to the first two runs, and finally you add on the iron bar. And again, my suggestion is to try and keep it as consistent as possible. So you move this here, make your measurements, and discuss your observations. Once you've done this part, you're going to decide which configuration had the most best response, and then for your final part of the experiment, you're going to compare a 400 wind coil with 200 wind, 400 wind, 800 wind, and 600 wind, and see which ones are step up and step down transformers. Okay, so for part A, we are going to be working with a coil pack and a magnet. You did this before with your magnetic fields exploration. Now we're going to really explore Faraday effect in full detail. Before we set it up, we're going to go ahead and take a few data points. I'm going to boost this up to about 250 hertz. That should be enough, and if we need more, we can always boost up a little bit more. I'm going to hit start. And you can move the mass around there, no big deal. But this is the main key here, so drop this south side first. You don't want it to be too high from this, and you don't want this to be too high from the safety pad. So just about a little bit, about an inch maybe. And maybe the person who's either dropping the magnet or holding the pack is also the same person doing the other. So it's one person dropping it, but everybody takes turns throughout the course of the experiment. And we drop it, 3, 2, 1. That was not good. 3, 2, 1, like so. And then we've got our data. Let's take a closer look at it. So now we come into this data point, and we're going to go ahead and let's take an active data. Click on the active data box. I'm going to go down here and just capture the drop that we're interested in. And then we can rescale. May take a couple tries to get it to work right. There we go. And you can see the smoothness of the curve. Shorten this down just a little bit, spread this out. We want to really widen this up. So I'm gonna actually delete this box now because it's too big. Now that I've got it spaced out the way I do, you can see that this curve is not. You can see that this curve is not got a simple shape to it. There's complexities there. So one thing that we want to do is, this time we're going to turn on the area under the curve because we want to actually have, this is voltage versus time. So voltage times time should be the total flux passing through. So we're going to click on this and we're going to see if the flux is the same. You see that it gives an area under the curve, a preset area under the curve. But I just want to zoom in for just a moment so you can see that it's taking into account all the area under the curve, both all the way back to the beginning, plus all the stuff that's already off screen, but it's still part of the data. So what we need to do is narrow our focus a little bit. You see how this one seems to cross right around, what's this point here? Let's just throw a mark on that one. That'll be our starting point. You know, this is just to make sure we're not taking into account. Another thing we can do is before the data run, make sure to calibrate or zero out the sensor. Zoom back out so that fills the screen, and now we turn on our active data block. I'm going to set it right here. I think for this data set we would have done well to go with a 500 hertz data roll. And now you can see the area that's marked out is a negative 0.057 volt seconds, or in this case flux, the general amount of magnetic field that's passing through the coil during this period of time. And then you'll record this down, and you'll move this over to take up a similar amount of area, well, to take care of all the data points that are above 0. And you can see that gives an area of positive 0.058. Now you'll have similar areas, but one's negative, one's positive because of the way that they're laid out here. What does a negative area mean? It means negative area times positive, negative voltage times positive time, which means negative voltage from Ohm's law, negative current. So the current goes the other direction in this region, goes in the negative direction, whereas after it's halfway through the drop, whereas for the second part of the drop, it is going positive in some orientation of positive for the circuit. So you take the absolute value of those, compare those by percent difference, and see how well in agreement they are, and then you'll do the same thing with your magnet flipped upside down. One thing you'll notice is that the peak here for the second one is a little bit taller compared to the second one, so you're going to see if that's also true for yours. What's happening during the motion? Let's really take this apart. One of the things that we want to be as scientists is observe everything and ask, is it important or is it not? Even though the negative is down low to, what is this? Negative 1.26, this positive value maxes out at, let's move this out of the way, 1.979. So the maximums are vastly different, and the shape of the curve is changed based off of this adaptation, but the area should be coming out calculation the same. So the question is, why? What's happening as the magnet's moving through there that would account for this? Remember, what does the actual data mean? This is a higher voltage in this later part of the data collection compared to a lower maximum voltage at the first half of the motion of the magnet. So think about what that might mean. For part B, we don't need this signal anymore, so we can go ahead and click on this, and we're going to delete the display or cut the display. Either way is fine. We don't need that anymore. And we're going to bring down a new one that you haven't used before, scope. Just a short way of calling it a oscilloscope. And we need to set this one to voltage, and we want to add new y-axis to the scope display. We'll set up a voltage sensor, set that to amplitude 1 is fine, auto, close. Once we've got the display set, we can go and take some data. And so I've got here, you've got the two blocks that are different coil packs. They may be the same. This is part B. And so with the oscilloscope, you'll be looking at the voltage from the output device as well as from the sensor based off of their proximity to each other. And you're going to test the different blocks there, and then choose one that you think is the best one to work the configuration. So I've got these two beside each other. Output voltage again is the power coming out of the power supply going to the 400, so it's creating a current in there using a sine wave. And then the 1600 is still set up as a probe to pick up the voltage sensor, and that is going to be voltage channel A. So let's go ahead and hit record. And you see you've got some data on the point. When we come over to this data, right now the two scales, the left scale and the right scale, are scaled to each other, so you can see that this is not as big a pickup. And then you'll turn them in a certain way according to the instructions. Don't follow this particular instruction at the moment, just the idea of turning them to face a particular and consistent way. And we record again, and you can see there's a different response. And only thing that I really want to show you is a couple things from this, because I'm going to leave this configuration going. I'm not going to demonstrate the setup at this point. Let's hit rescale here. You see now it makes it look like they're the same scale, but on the left side we're going on a scale of 1 volt. This is the output voltage. And on the voltage channel A, that's the 1600 in this case, we got a voltage almost of 2. So make sure that you're paying attention to the actual voltages. But one thing I want to show you is this area over here at the front. So I'm going to hit record again. And you see there's a different character here. Let's zoom in a little bit on that. There's a little bit of different character before it falls into operation. Some of you will see out of phase, some of you will see in phase results from this. This is just a matter of the circuit being flipped around. But the thing I want to show you is this little bit at the front, because one of your questions is, what about this bit at the beginning, this first part of the cycle, before it settles into a complete cycle. Hit repeat. You'll see that it changes. Now there's some extra noise that's coming in there, and this is the, now this is excellent for the, notice that there's some kind of a noise coming in on the input channel that seems to be semi-regular, but does it show up on your pickup channel? And that's probably going to be very informative for your 400-400 packet comparison, also known as the isolation circuit. So, but pay close attention to what's happening at the very beginning. Every time you hit a cycle, you don't have to save them all, just make sure you print 1 or 2. And see if you get an answer about that. In this case, notice this noise is here, but it doesn't really show up elsewhere. So the rest of everything else is pretty self-explanatory, but this should give you a quick insight into what you're dealing with when you're working with this software. Well, that does it for this week's walkthrough. I'd like to remind everybody, if you have any questions about these concepts, you can always talk to me. You can talk to your lab TA. And until next time, we'll see you in the lab.